Geo Academy, and today we are going to start with the topic what is metamorphism. So, first we need to know why shall we study metamorphism? Or why do we need to study metamorphism? It is because the first point is the interpretation of the conditions and evolutions of the metamorphic bodies, mountain belts, and ultimately the state and evolution of the Earth's crust. So, as we all know, that metamorphic rocks are formed when their protolith undergo a lot of pressure and temperature. The protolith means the primary rock which was subjected to pressure and temperature conditions to be metamorphic rocks. So when we find these metamorphic bodies, it's clear that they have undergone a certain pressure and temperature conditions. So we can interpret those conditions. Mountain belts, when mountain belts are formed, there is a lot of deformation, there is a lot of pressure and temperature rise due to friction between planes, due to the stress is formed, compressional stress, depressional stress, all the stresses are formed. So when the stresses are formed, they will affect the regional rocks and turn them into metamorphic rocks, isn't it? So those metamorphic rocks, if we find and feel, we can easily say that there was an orogenic belt there at some point. So this interpretation is important. Obviously, this is the most important part of metamorphism. We'll see it later on in this video. Ultimately, the state and evolution of the Earth's crust. So, the Earth's crust was not always as it is today. So, examining the metamorphic rocks, we can date back the paleoclimatic conditions or the paleo conditions. We should not say climatic conditions. That's a term more often used for weathering. So, paleo conditions that existed when the Earth was in its geological journey during the past. So we can just make out of it. Metamorphic rocks may retain enough inherited information from the protoliths to allow us to interpret much of the pre-metamorphic history. So again, that's the same thing. It's just written as a different point. You can all understand that this protolith means the rock that originally existed and was not under any pressure and temperature condition. So as we all know that due to pressure and temperature conditions, not all the minerals of the rocks get deformed or get transformed. Some of the minerals do occur as the same mineral and they are slightly metamorphosed, like their shape gets changed. They try to recrystallize themselves, but often some minerals still exist, as we can see in partial melting. Let's see, say if a rock has got three minerals A, B, C. If A is resistant to a particular pressure temperature, then it will continue to appear in the rock on about a period of time or a period of pressure temperature increase. So it's not getting affected. So presence of A can help us determine the protolith of the rock. So that's called the pre-metamorphic history. Pre-metamorphic history is the state of the rock before it was actually metamorphosed. So what is metamorphism? Metamorphism is a sum of all transformations which cause a rearrangement of the elements of rock at the atomic scale, leading to a recrystallization in the solid state, with or without a fluid phase as a result of variation in temperature, pressure, or of composition. So what's being said here is metamorphism is a sum of all transformations. It is a set of transformation which causes a rearrangement of the elements. Since the elements at an atomic scale, if we see, the rock is composed of an element of a mineral, and those minerals in turn are constituted by the elements. If these elements can subject a particular temperature pressure, then they persist in the rock, and if they don't, they try to recrystallize themselves. They try to change the form of the elements. Means element A and element B and element C, maybe they form a particular mineral, and when we increase the pressure temperature, then maybe C just diffuses out of them, or just melts out. So then only A and B are left there. So if A and B are left there, then they constitute a different mineral, ain't it? So at an atomic scale, this is a deformation, means a very subtle deformation, means it's not containing the all the minerals. Means some minerals are getting out. So that's how metamorphic rocks are formed. And also you can consider that ABC all exist, but after certain uh, temperature and pressure, this mineral just changes its crystal form. If it was cubic, now it has become hexagon, like that. If that happens, then that is called recrystallization in the solid state, leading to a recrystallization in the solid state, with or without a fluid phase. Means they may or may not contain any water or gas in them. As a result of variations in temperature, pressure, or of composition, actually this composition is a result of temperature and pressure indirectly. But we will later also see that this composition may also change due to incursion of fluids, of hydrothermal fluids and some other fluids like that. So they are not considered as metamorphism, though they are considered as metasomorphism. So we'll come to know later on about them. This definition of metamorphism excludes the process of surface alteration, which are functioning both at the atomic and ionic scale, lead chiefly to the destruction of rocks by leaching and mechanical disaggregation, and not their transformation. So what is said here is that surface alteration, like the processes of weathering, diagenesis, etc., are not considered a part of metamorphism. Why? Because they function both, means they lead chiefly to the destruction of the rocks by leaching and mechanical disaggregation. It's not just, means if we have a rock there, it's composed of some minerals, some grains, and what this surface alteration do is either they just chemical leaching, means some chemical falls in here, it just dissolves the rock, it dissolves some minerals out of the rock and takes it away. So the remaining part is left untransformed. Means the other minerals remain untransformed. Only one mineral gets eliminated away from this rock. So what is the difference? That the entire rock is not getting transformed. Obviously, it's lacking some mineral now because it's being some mineral is being washed out by some type of chemical or some weathering agent. But the remaining that is left is not altered. Even if it is altered, then it's not the alteration of the pre-existing mineral. It is that some mineral just came in and just took its place. It's just replaced it. Okay, so it's not considered metamorphism. Metamorphism is like if this is A, this has to change to B. There is no alteration. This is not like this. A reversible B. This always A changing to B. So that is known as metamorphism. This definition of metamorphism excludes the process of surface alteration, which is functioning both at the atomic and ionic scale, lead chiefly to the destruction of rocks, so leaching you understood, and mechanical disintegration. What is that? Means this is a rock, there is a stress, the rock breaks down into loose sediments, unconsolidated sediments. This is known as mechanical disintegration. And so this is also not considered a transformation, it's just a breakdown. Transformation means one mineral changes to another mineral. Okay. So we go to the next slide. The above definition includes. So what does this definition include? What does this surface alteration mean? These surface alterations include diagenesis, the process which changes unconsolidated sediments into sedimentary rocks. Unconsolidated sediments are there like this, and under diagenetic pressure, or that may be a lithostatic pressure, they get compressed and they are compacted to form a rock, and this rock is known as a sedimentary rock. This is a sedimentary rock, and this is not basically a metamorphic rock. So this diagenesis process cannot be included in metamorphism. Diagenesis consists in large part in reduction of sediment porosity by compaction. It's obvious that if you the sediments are like this at first, and they maybe are having pore space at the present, but when a stress comes upon like this from all sides, then this is simply gonna be squeezed, and if this is squeezed, then the rock, the spaces will get consumed up. These particles will come more close to each other, and these pores will no more exist as they already have been taken up. The volume has shortened. Diogenes also implies recrystallization. This is also a type of recrystallization, ain't it? A rock was there, it has broken down into sediments, and after being broken down, they are again consolidated by some force or some pressure. So this is a type of recrystallization. If you see metamorphism here, here is a term called recrystallization. But so we cannot say that this recrystallization that we are seeing in diagenesis, this shouldn't be mistaken as metamorphic process. Mechanical integration is not considered as recrystallization. So metamorphism generally takes place at higher temperature and pressure conditions than diagenesis. That's obvious. Metamorphism is a high grade process than diagenesis. The intrinsic nature of the physical chemical mechanisms is the same for both processes. Means the intrinsic nature means both are subjected to external conditions like pressure and temperature. Metamorphism is generally related to orogenic or pre-orogenic phenomena. Yes, this is important. See, metamorphism is generally related to orogenic or pre-orogenic phenomena, whereas diagenesis is related to the dynamics of sedimentary basins. This metamorphism requires a lot of pressure and temperature, ain't it? So, lot of pressure and temperature, where can it evolve? It is obviously that if there is a huge deformational activity going on, like in a mountain building process, there is a lot of stress, there is a lot of temperature due to the friction between plates, there is a lot of stress due to the collision of plates or uh, folding of belts or beds. So then there is a high temperature and pressure condition. That is a high grade terrain, and then there is metamorphism prevalent. Whereas diagenesis is related to the dynamics of sedimentary basins. Means diagenesis sedimentary basin is there like this, and the sediments are getting deposited like this. They are coming down and they are getting deposited here, depositing, and at a time, this pressure is gonna compress the sediments here, and what will happen is that they will form a sedimentary rock bed. Okay, so this is also a type of recrystallization that we were talking about in the previous slide. So basically, this is diagenesis. This process is known as diagenesis. Takes place at lower depths, at lower temperature pressure. But, but, the next point is interesting. This distinction is extremely subtle because sedimentary basins precede, follow, or accompany orogenesis, and the dynamics are therefore later. So here you can see this is a mountain valley, right? And this is formed after the mountains are formed. So basically, what they mean to say is that these two phenomena, diagenesis and metamorphism, go hand in hand. Sedimentary basins were formed. Then also it can happen that due to stress, these beds were folded to form mountains. And it's also possible that after these fold beds were formed, at this basin the sediments got deposited. So it's either way, or both may occur at the same time. So that's what it's said here. That so it's basically difficult to differentiate two on the basis of their uh, means what they're associated with, orogeny or sedimentary basin. So it's very difficult. This distinction is extremely subtle. This is what is important. Subtle. It's very indistinct, though distinct. It's indistinct, but it's distinct. Very small differences there, but you cannot just differentiate them. So that's how you can explain this word subtle. There is incontestably a problem in defining the limit between metamorphism diagenesis, which may not always be clearly resolved. It may differ from place to place. If you see a subduction zone, metamorphism can occur from here, even at the lowest depth, shallowest depth, because here there is an influx of water, here is a subducting plate, so here will be an increase in temperature due to friction, and also there is influx of water, and with this due to this friction, a stress will also act between these two plates, a shearing will act. So here metamorphism can easily take place, but and so if we go further away from here, then we can see diagenesis is also occurring here, because but there is no deformation or plate tectonic movements here, so diagenesis is occurring here, and at the same depth level metamorphism is occurring here. So it depends upon the plate boundaries, and it also depends upon the type of phenomenon that is occurring. Means if here it's only deposition occurring, then you will have a diagenetic terrain, and here as you can see there is deformation occurring, so you will have a metamorphic terrain here. So it's hard to define a perfect boundary that this depth is metamorphic depth, diagenesis depth, and this depth is metamorphic depth. You cannot just say like that. Yeah. Next part is that the domains of diagenesis by the crystallographic properties of the light part. So we'll come to this later on. Okay, we'll do it now only. Domains of diagenesis, the right part of the figure portion of an X-ray diffraction. So that's how diagenesis, ankizone, and epizone are divided on the basis of different isotopes of a particular mineral called illite. These are the crystal faces. Okay. 002 to see. Metamorphism and migmatization. Metamorphism, process of recrystallization in the solid state, is in principle distinct from magmatic phenomena, participation of a silicate liquid. What is this actually? Is in principle distinct from magmatic phenomena. It does not involve a fluid, for example, an acidic fluid or a silicate fluid. Metamorphism, the process of metamorphism does not involve this. In domains of high-grade metamorphism, the temperature is sufficiently high to allow partial fusion of the material and the production of liquids, generally of granitic composition. So what's this saying is that in domains of high-grade metamorphism, means where the temperature and pressure are very high, the temperature is sufficiently high to allow partial fusion. What is partial fusion? Fusion means melting of the material and the production of liquids, generally of granitic composition. So let's understand that figure. Let's say this is a high-grade metamorphic domain, and we have a material there of granitic composition, right? And due to the high temperature, these some of the minerals just melt out. This process is known as partial melting. So some of the minerals do melt and give rise to a granitic melt. Now, we are discussing about this? Because in the first line we have said that metamorphism is distinct from magnetic phenomena. In magnetic phenomena, there is also partial melting involved, but it's not just partial melting. The full rock may also melt. Actually, the full rock melts to give a magma. But in metamorphism, what it happens is that due to increase in temperature, some particular portion or some particular minerals will melt, and this aggregation, this melt will result in a granitic melt and or have a granitic composition. So if these liquids remain enclosed and crystallize within the rock bodies from which they were derived, they result in a mixed formation or migmatites which belong in the metamorphic domain. So if these liquids that are formed remain enclosed, means see, if this is a rock, there is a chamber, and this particular chamber is surrounded on all sides by the more resistant minerals, then what will happen when this rock melts due to high temperature? It's getting enclosed within this case of the resistant mineral, so it will persist in the rock and again recrystallize when the temperature subsides down. Okay, so what will happen is that they result in a mixed formation. These rocks are called migmatites. Actually, migmatite is a rock like this. I went to a field. I didn't. I don't think I have the image in the computer. So, okay, let me show you what migmatites are. Okay, no, this is not a good image. Yeah, see this one. Even this one, you can just, it looks like spotted. This is not a migmatite. A typical migmatite. Typical migmatite. Let's see if we can find out here. This is a quartzite basically. This is not a migmatite. Migmatite. This is also not a migmatite. So I'm not getting a good picture here. It is a more granitic composition. The one I had was an alkali composition. You cannot explain it from here. It's not very firm. It looks more like a nice. Right. Magnetite. Okay, let me illustrate and show you. A migmatite is basically a rock like this. You see a lot of dark minerals thicken it. A lot of dark mineral like this. And a lot of light patches like this. These dark bands are known as the melanosomes, and the light ones are known as the leucosomes. So you can easily identify them like this on the field. And when you do so, it's when we identify these rocks, actually the darker ones, if they are formed above, if the melanosomes appear above and the leucosomes appear below, it's on the lower side, then it shows that means if the melanosome concentration is high, it refers to a very high grade metamorphic pigment, and if the melanosome concentration is low, then it refers to a very low grade metamorphic pigment. This somewhat it happened, slight metamorphism as occurred. That's what mcmatite makes. Oh, here's a nice, nice picture. I forgot that I've given it here. See, these are the dark bands. You can basically zoom it out and see this part. See this part. Yeah. Its leucosome concentration is more. So this is a low-grade terrain. This low grade of metamorphism took place here, and if you basically see this one, then the grade of metamorphism was higher. So the melanism concentration is higher. Let us move on to the next slide. Metamorphic rocks were once igneous or sedimentary rocks. That we all know that any rock, any rock can break down on weathering to form a sedimentary rock. A sedimentary rock may be subjected to melting at depths, means that is known as the subduction of a plate, or a plate gets extinct like that. So when the plate is getting extinct, these sedimentary rocks are getting into a pool of magma and they get melted, and again they crystallize to form an igneous rock. And both of this, the sedimentary rock and the igneous rock, may come to a somewhat high pressure, high temperature terrain to produce a metamorphic rock. So that's obvious that there should be either sedimentary rock or metamorphic rock. Or even in the metamorphic scale, they can be differentiated as high grade and low grade. Okay, so metamorphism is a process that occurs in solid rocks. Metamorphic rocks must have formed from pre-existing igneous or sedimentary rocks. Metamorphism is a process that occurs in a solid rock. Obviously, it has to happen in a solid rock. No melt. Like in a igneous rock, a melt is giving rise to a solid, and so metamorphism, it doesn't happen like that. The solid gets transformed to another solid. Just that. During the process of metamorphism, their original igneous or sedimentary minerals broke down, and new metamorphic minerals formed. That is the transformation we are talking about, from one mineral phase to another mineral. There may have been more than one cycle of metamorphism with metamorphic rocks forming older metamorphic rocks of an earlier cycle. That was I was telling here, like A metamorphose to B, metamorphose to C, metamorphose to D, like that. So B is the older rock from which was older metamorphic rock which was metamorphosed to form B. We call the original igneous or sedimentary rock the parent rock or protolith. Obviously, the revision I have already told you in the previous slide. In the very first slide, what does protolith mean? If the process of metamorphism has been intense, or if there have been several cycles of metamorphism, we may find it difficult to discover what kind of the rock the protolith was. Yeah, of course. Now, for example, when you were a kid, means you were an infant, you looked something different. Right? This is A, this is B, this is C. So let's take a grain, and it has metamorphosed a multiple number of times. So what will happen? The pre-metamorphic history will be erased with time, right? Yeah, the example I was talking about, that when you were an infant, you look totally different, and today if you if anyone asks in front of you, taking a photograph of yours to anyone else, that do you know this guy, then he will say, no, I don't know this, no, I don't know him. So means that the transformation has occurred in you, and they are so diverse from the one that were prevalent when you were an infant, are totally mismatching. So it's nearly impossible to know that it is you from that photograph, right? So that is the same sort of thing that happens to a protolith. When a protolith is undergoing a lot of metamorphism, then what will happen? The pre-metamorphic history is going to be erased. If the process of metamorphism has been intense, there have been several cycles of metamorphism, and find it difficult to discover that kind of rock was the protolith. So it's very obvious. I hope you understand this. Protolith are the parent rock. See, shell to slat, shale to cyst, shale to gneiss. So shell is the protolith, common protolith, and this is the grade of metamorphism. This is increasing. Okay. So shell first forms lead, then forms schist, then it forms gneiss. So slate forms schist forms gneiss, or sometimes directly shell can form gneiss. Okay, it's not obvious that it has to go through all this phase and become gneiss. And if you see limestone, it gives rise to marble. Sandstone gives rise to quartzite, and basalt. Yeah, that's an interesting one. See how many different metamorphic grades it has got. Green cyst, greenstone, amphibolite, granulite, eclobite, nice. Sorry, nice is granite. Till here, eclobite. So you can see these are the grades of metamorphism for basalt. It's not like that it cannot come directly here, but it's obvious for a long range of is it has to travel a long pressure temperature transformation. So obviously it cannot just go directly there. Generally, theoretically it's possible, but in real it's not that easy. So green cyst is gonna turn to greenstone with further increase in pressure temperature. Greenstone is gonna form amphibolite. Amphibolite is gonna form granulite. Granulite into eclogite and so on. Eclogite is the highest temperature pressure metamorphic form of basalt. Granite, it forms gneiss and charnocite. The spelling is wrong. Charnocite is just K will be there. Charnokite, charnokite. So granite and charnokite. Granite, gneiss and charnokite. So granite in the form gneiss to charnokite, or granite to charnokite. So basic idea of that as well. Classification and nomenclature. Thus, the main criteria for naming rocks are the composition of the protolith, palitic, semitic, semipalitic, marble, etc. The metamorphic minerals present in the rock texture, especially grain size, example distinguishing the members of the series slate, phyllite, schist, gneiss. For coarse-grained rocks, the presence or absence of compositional banding. We can modify the names if there are any notable minerals in rocks, example kyanite, schist, tremolite. So nomenclature we are talking about in this slide. Nomenclature, classification, nomenclature. See, classification of and nomenclature of metamorphic rocks are quite easier as compared to igneous and sedimentary rocks. That is because we just use our own language to nomenclate these rocks. Obviously, based on the minerals that it's containing. See, here it's the protolith. We have to first identify whether it's pelitic, semipelitic, marble, etc. The metamorphic minerals present in the rock. Okay, so this basically the minerals that are found are like chromites. There are some index minerals. We will come to it on our next lectures. and then we will discuss about those minerals that are found in these rocks. So take this example: slate, phyllite, schist, gneiss. What is said in this point is that this textured, specially grain size example distinguishing the members of the series. If you investigate a bit, you will know that slate, phyllite, schist, and gneiss are of all the same composition, and the only difference they have got is in their texture. So that's how we can differentiate the rock, although with the same composition. For coarse grained rocks, the presence or absence of compositional banding. When the rocks are coarse grained, you will not find any particular banding, dark, dark, light, dark, light, like this you will not find. But like here you see dark, light, like this banding you can see. This type of banding you will not see in coarse grained rocks. This is a fine grained metamorphic rock. Yes, and we can modify the names if there are any notable minerals in the rocks. See, this kyanite is a index mineral. Tremolite marble. Tremolite is an index mineral in a metamorphic rock. We also have sillimanite, andalusite, chromite as index minerals. So we'll come to it in the next lecture. We also give some rocks such as hornfels special names. We will see in the next slide. Hornfels basically we have are of different types. We have a separate class on that later on. So here see this table here. The basaltic gabbro, see here. Let's come to gabbro. Plagioclase, feldspar, amphiboles. These are the minerals, main minerals. Okay, fine grained, less than 0.1. This is the dimension of the grain, or the diameter of the dimension of the diameter of the grain. Medium grained, this is the dimension, and the coarse grained, this is the dimension of diameter. So what we are doing is that we are going to basalt of gabbro. We are seeing that green cyst occur in these dimensions. Green cyst and crystal also occur in these dimensions. And basically all this occur in this coarse grained band. So this is the protolith. If the rock is fine grained, we are going to get this minerals in its metamorphosed form. If the rock or no, sorry, this is the main mineral that is there. And we are going to get green cyst and green stone on the basis of grain size. We are gonna get green cyst and green stone if it is medium grained, and we are going to get amphibolite, basic granulite, and eclogite if it is coarse grained. And if they are banded, obviously you can see hornblende gneiss, pyroxene gneiss. Gneiss means banded. We will see gneissic bands in gneiss. See, gneiss you will find throughout this column. Gneiss, banded marble, here only it's an exception. Calcareous gneiss, granitic gneiss, ultrabasic gneiss, foliated peridotite, foliation. Foliation planes are there. They also form bands sometimes. So what are metamorphic minerals? The minerals in metamorphic rocks are usually new crystals formed by chemical reactions that occur during the process of metamorphism. What they say, the minerals in metamorphic rocks are usually new crystals formed by chemical reactions that occur during the process of metamorphism. However, many minerals are already familiar in sedimentary and igneous rocks, example quartz, calcite, feldspar, and mica. We only find other minerals in metamorphic rocks. Example, glaucophane or occur more commonly in metamorphic rocks, example garnet and epidote. What's their mean to say is that mineral or metamorphic rocks are usually new crystals formed by chemical reactions that occur during the process of metamorphism. Chemical reactions that have occurred during the process of metamorphism, they are responsible for these mineral transformations. And we are going to get many popular minerals in metamorphic rocks that are identical to those that are found in sedimentary and igneous rocks, right? So we only find other minerals, and this I was telling you, glaucophane, kyanite, andalusite, sillimanite, all these minerals are known as index minerals for indicating minerals for metamorphic rocks, because we also found all these minerals in quartz, so sedimentary and igneous rocks. So how to differentiate? We differentiate them using this glaucophane, kyanite examples, etc. Garnet in epidote. These minerals, these are very good minerals. They show in fact a recrystallization. Epidote means indicates very high temperature and pressure terrain. Crates 1973 proposed a scheme of 2 or 3 letter abbreviations for metamorphic mineral names. Example, SPH for spin, and such schemes have since been widely adopted in both textbooks and research. Here we are talking of Winter, okay? John D. Winter. Creates the actual abbreviations. See, these are the actual abbreviations. We use olivine as OL, fusterite as F4, spin as SPH, almandine, this is also a garnet, pyrope is a garnet, spessartine is a garnet, grossular is a garnet, andradite is a garnet. These are all garnet group of minerals. If you see, they all have Si3O12 as the common part, and the cations differ, okay? The cations are different. Magnesium and aluminum is there, then it is uh, pyrope. If iron and aluminum is there, it is almandine. If manganese and aluminum is there, it's spessartine. If calcium and aluminum is there, it's grossular. And if calcium and ferric ions is there, here they are written wrong. Actually, this would be Ca3Fe2. Just correct it, because Fe2 plus Ca2 plus Fe3 plus. So crisscross is Ca3Fe2, Ca2Fe3. Sorry, Ca3Fe2 it would be. This Fe3 plus. Just cut this 3 plus. Here the crystal forms are given. This is cubic, D36, H6, 7.5. These are crystal orientations. These are further details in there, given in further details. Hand specimen properties, actually this is the shape, this is the index according to the book. These are the colors, cross polar colors. Let's study a bit in details. The aluminate silicate groups, they are also found in metamorphic rocks, as I was telling you: sedimentite, kyanite, andalusite, storolite, chloritoid, laurite, spurite. Like those these minerals are also found in metamorphic rocks, and they basically are denoted by these abbreviations: SILKY, AMD, andalusite, storolite, ST, chloritoid, CLD, yarnite, LAR, sporite, SPO. These are the disilicates. Means there are two silicate forms. One is Si2O7, one is SiO4. So they are termed as disilicates. This is Si2O7, SiO4, Si2O7, SiO4. Easily understand. Here it's Si2O7, Si2O6. They have written it in a resultant form, means in a short form. It's same as this. This is Si2OH. Dot OH7, OH3, CO3, CO7. That's right. So these are the abbreviations. Tillite. Don't confuse it with tillite. Tillite is a rock, tillite is a mineral. I can see Si2O7 is common in all of them. 2CaCO3. Carbonates are there. You can take screenshots of these pages. Yeah, this is a very important. Come through this one a lot of times. The orthopyroxene group. The orthopyroxene group, we all know. Acetyl hydroxane, orthopyrrolite, clinopyroxene group, clinopyrox, calcium pyroxene dioxide, Hardenbergite, amphicite, jaditite, elastonite, sapphirine. These are the common names you all know. Amphicite, Hardenbergite, dioxide, clinopyroxene, orthoferrosilite. Actually, ferrosilite we all know. Orthoferrosilite here. It's written the abbreviation. Muscovite, paragonite. So just take a screenshot. Zoom out so that you can take this. This is all this. Take it. Take this. Just make sure. Remove this. Taken. So the types of metamorphism, different approaches to classification. Based on principal process or agent, dynamic metamorphism, thermal metamorphism, and dynamothermal metamorphism. Right? Let's elaborate them. Okay, we will do this in the next class.